SwayamPrabha. Digital India. Educated India.
Good morning everyone. Now we will start a new module, efficiency improvement of power plant. In a conventional power plant, carbonaceous feedstock is used in the plant for combustion, and the combusted gas, that is flue gas, is used for the production of steam. So, high heat of the flue gas is used to convert water to steam, and that steam is further used for the production of electricity in steam turbine. But if we use gasification, so gasification based plant produces syngas, it can be further combusted, the syngas is combusted to flue gas. So, high amount of heat is released. So, this can be used either to steam production and followed by steam turbine, or directly this flue gas can be used in gas turbine for the production of electricity. So, there are two options in this case. Either we can use gas turbine followed by steam turbine, or only steam turbine, or only gas turbine. So, efficiency of the process will depend upon which step we are adopting. Not only that, there are many other factors which influence the efficiency, like say the preheating of the water which is used for the steam production here, whether water is preheated or not, whether air cooling or water cooling is used to reduce the temperature of the flue gas. So, there are different factors on which the performance will depend, and one important factor is that there are number of losses, and due to the losses the efficiency is reduced. So, in this module we will discuss the power generation, its flow sheet, performance of waste based power plant, factors influencing power efficiency, thermodynamic cycles for power generation, cogeneration and heat recovery, overall plant efficiency, and then we will discuss energy analysis of steam process and types of turbines and the cycles for power generation, working of combined cycle and efficiency improvement, and last we will see efficiency calculation through thermodynamics laws. So, now we will see the flow sheet for power generation. So, if it is a conventional power plant, that is combustion based, so we will be using some fuel, in this case waste and biomass. So, that will be used in your furnace or incinerator or gasifier, whatever it may be. So, in this case it is an incinerator, and in incinerator the primary and secondary oxygen is supplied. So, secondary combustion chamber is used to produce flue gas. So, this flue gas will come and we will use this flue gas to produce steam. So, this is water, flue gas will give us steam, and the steam will go to turbine, that is steam turbine along with the generator, and this flue gas after heat recovery in boiler, after the production of steam, it will be going for clean off, and to air. So, this is the flow sheet, and when we are getting the steam turbine, so its output will be condensed and will be recycled back so condenser it will be there and it will give the water for the boiler input. Now, this steam which is coming out from the turbine, that can also be sent to some cooling purpose. So, some cooling unit. So, this cooling unit will obviously the temperature of this will increase and again it will come to this. So, addition of this part is optional, and if we add this part, the performance of the power plant will increase. So, this is the flow sheet of conventional power plant. Now, if we use the gasification based power plant, obviously this secondary combustion will not be there. So, we will be having the gasifier here, and this will be directly used for gas turbine for the electricity production. So, it will directly go to gas turbine. Before that it will give a syngas. So, that syngas will be reacted somewhere with the oxygen. So, high temperature will be generated and pressure will be generated. So, here the temperature is around say 150 degree centigrade to 1800 degree centigrade. So, that gas turbine will give us electricity. So, this is the flow sheets for the production of electricity in the power plant. Now, if we think on energy perspective, then we will see that waste or biomass or any feed that will give us flue gas and solids, that is ash and slag. So, this is not desirable, this ash and slag is not desirable, it will reduce the efficiency. So, flue gas which is produced, that will be used in boiler heat transfer and it will give up steam and actually we will get the electricity. So, electricity will get. So, in this process if we see, then the performance, the overall energy production in this plant will be guided by many factors. The first one, the secondary combustion chamber, what type of fuel we are using, now what is the heating value of this waste or biomass or any carbonaceous feedstock. Then what is the efficiency of this reactor, like whether we are using incinerator or gasifier or type of incinerator, type of gasifier like fixed bed, fluidized bed, entrained bed, all those things will influence the efficiency. Then heat exchanger in boiler. So, boiler efficiency will also be responsible, and then you will see it is coming to turbine and generator. So, efficiency of turbine and efficiency of generator will also influence the overall performance. Then it is coming to condenser. Then in condenser, what type of fluid we are using, whether we are using air or whether we are using water, that will also influence the overall performance of the process. Here, whether this heat available in the outlet of the turbine is used for the recovery, heat recovery or not. So, that will also influence the overall performance of the process. So, these are the heating value of the waste, efficiency of the thermal processing unit, thermal efficiency of the boiler, efficiency of the turbine generator, energy requirements of the air pollution control system. So, here the air pollution control systems are there, the exhaust pollutions is going to the environment after proper treatment. So, what amount of energy is required, that also influence the overall performance of the process and any other in place energy uses. Now, I will see how can we quantify the performance. So, to quantify the performance of the process, we have two parameter, one is heat rate and another is thermal efficiency. So, heat rate is related to, it is the ratio of fuel energy input to electrical energy output. So, how much fuel energy is given as input to the plant within certain time and how much electricity is generated within this time period, the ratio is heat rate. So, heat rate HR is equal to, it is the ratio. So, heat, we are giving the input to the plant, that is heat input in certain time divided by how much energy we are getting. So, energy output in the same time. So, this is kilocalorie and this is equal to kilowatt hour. So, this is the unit of heat rate. So, what is this heat input? That means what is the amount of biomass and waste we are using, that is MC into calorific value CV of the material, how much materials we are using and the calorific value, that is the total heat input, and within this time period what is the energy generation rate, energy generation rate into time. So, this is our HR or heat rate. Next we will see the thermal efficiency. So, thermal efficiency can be defined as the ratio of energy generation into time divided by the heat input from the feedstocks. So, this thermal efficiency is energy production rate into time, that is energy produced divided by how much energy is given, MC into CV. That is actually gives us some idea what is the design value and how much energy we are getting. So, that is the ratio of this. So, this can be written as, and as we are interested to get it in terms of percentage. So, we will multiply this into 100. So, this is equal to, we are getting 100 divided by MC into CV divided by energy production rate into time. So, this is nothing but HR in kilocalorie per kilowatt hour. Now, we know that 1 kilowatt hour is equal to 859.8456 kilocalorie. 8456 kilocalorie. Thus, if we want to get the thermal efficiency in terms of percentage from the heat rate, so then we can write it, this is equal to 100 divided by HR in kilocalorie by kilowatt hour unit into this conversion factor. So, that will be 859.8456 in percentage. Now, let us calculate one thermal efficiency of a plant. So, it is given, let us see the statement. If the average heat rate of a power plant in 2015 is 2611, HR is equal to 2611 kilocalorie per kilowatt hour. So, kilocalorie per kilowatt hour. Then we have to calculate the average efficiency of the plant. So, average efficiency, thermal efficiency is equal to, we have got 100 divided by HR in kilocalorie per kilowatt hour into 859.8456 in percentage. So, in this case 100 divided by 2611 into 859.8456 percentage. So, that is equal to, we are getting around 33%. So, that is equal to 33%. So, now we have seen how to calculate the thermal efficiency on the basis of heat rate and the energy supplied and how much energy we are getting from the thermal power plant. Now, we will see the factors which influence the power efficiency. So, turbine types and boiler design significantly influences the power efficiency, and conventionally the 40 bar oblique 600 psi pressure is used for the production of electricity in thermal power plant, and typical efficiency is say 35%, only 35%. So, the pressure of the steam if increased say above supercritical conditions, that is 221 bar and say 374 degree centigrade above this. So, here in this case the efficiency increases. So, 35% it can be increased up to 60%, 63%. So, the type of condensing device. So, type of condensing device is also responsible to give higher efficiency. If we use water for the cooling or air for the cooling of the flue gas, we will get different efficiency. We will get different efficiency for air and water. Now, the heat source to preheat combustion air. So, if we use some combustion air that may be preheated, so in that case the efficiency somewhere we can preheat it and somewhere we may not preheat it. So, the efficiency will vary. The steam or energy recovered on flue gas. So, the flue gas which is used to produce steam, after that also it is having in high temperature, and that temperature can further be used to recover energy from the flue gas, and if we use that option then it will improve the efficiency. And the last is the number of boilers are used and turbines we are using in the process. So, number of boilers and turbines if more, the efficiency will be more. Now, we have come to know about the performance of the thermal power plant in terms of efficiency. Now, how can we quantify and how can we understand in a better way whether the process can further be improved, the efficiency can be improved or not. So, this understanding will be developed if we know and if we learn about different thermodynamic cycles. So, for steam engine just steam turbine, for steam turbine the Rankine cycle is basically used to understand this steam turbine cycles. So, in Rankine cycle, if we develop the temperature entropy diagram, then we will see it consists 4 steps. The first step is your adiabatic compression. So, first step is adiabatic compression, and second step is your we do some expansion. So, isobaric expansion, isobaric expansion. So, isobaric expansion, it will go like this. So, 1, 2, 3 and we will get 4, and this is 4 dashed, 4 dashed. So, this is the diagram of our Rankine cycle. So, in this Rankine cycle we are getting first step, this is our second step. So, first step is because of the pumping of the water. The second is the boiler, in the boiler temperature increases, then boiling takes place, then steam pressure increases and temperature increases. And the third is adiabatic expansion. So, adiabatic expansion means the turbine performs reversible adiabatic expansion of vapor, the steam which is generated, that is sent into the turbine. So, the expansion takes place in adiabatic condition, and that is your 3 to 4. Now, in ideal condition this should be vertical line, so that the losses will be less, but in reality this does not happen. And the fourth step is the condenser transforms the vapor to liquid in a constant pressure heat transfer process. That means, after the electricity productions in the turbine, the exhaust from the turbine is a steam. So, that is condensed, and the condensed water is recycled back. So, isobaric compression, this is the fourth step of this Rankine cycle, and in this Rankine cycle this is ideal. This 1 and 2 vertical line or isoentropic operations are ideal conditions, but in practice the ideal condition does not exist. So, efficiency decreases. So, maximum efficiency we will get when this cycle will follow. Now, we see why the ideal condition is not achievable, we not get the efficiency as per the ideal Rankine cycle, because there are some heat losses in the processes as well as there are some friction losses. So, frictions, due to the frictions, when the steam is flowing through say piping or in boiler, that will loss, that will produce some losses. What losses? Friction loss, and friction loss will generate lower pressure. So, that will give lower pressure, and you will see that higher pressure is required for getting more efficiency. So, that is why the friction loss gives us lower efficiency and deviates from ideal to real conditions of the Rankine cycle. So, here the fluid friction causes pressure drops in boiler, the condenser and the piping between the components, and as a result the steam leaves the boiler at a lower pressure, just now we have discussed. Now, what is the efficiency of this Rankine cycle? So, what is the efficiency? Efficiency obviously the work output at turbine divided by Q input, how much heat we have given and how much work we are getting. So, this is giving us the efficiency. The maximum efficiency we can get by kernel efficiency 1 minus Tc by Th. So, in this case what is Tc and what is Th? Obviously, if we have one boiler, we are using the flue gas here, we are using water and we are getting steam. So, high temperature of the steam Th, we may use some heater also that is superheater. So, we are getting TH and this is our TC. So, this value is giving us efficiency. So, more the value of TH, more will be the efficiency, or lesser the value of TC will also give us more efficiency. That is why the supercritical condition, if the boiler is used, the steam is produced in supercritical condition, that TH is very high, then we get maximum efficiency. One example is given here. So, when steam turbine entry temperatures are typically around 565 degree centigrade and steam condenser temperatures are around 30 degree centigrade, then the maximum Carnot efficiency of steam turbine alone is around 63%, which is only 43% for a conventional coal fired power station. So, due to low steam turbine temperature, so due to the low steam turbine temperature with respect to gas turbine, the gas turbine the temperature is around 1500 degree centigrade, but here it is around, say, in supercritical condition 565 degree centigrade. So, due to this low temperature requirement for steam turbine, this is used in bottoming cycle of a combined cycle plant. Now, we will see the thermodynamic cycle, which is used to understand the working of a gas turbine. So, the gas turbine is represented by Brayton cycle. So, in this cycle we have again 4 steps. The first step, this one 1 to 2, this 1 to 2, this is the first step. So, this first step is isentropic process, ideal one. Then the isobaric process, then 3 to 4 we are getting again isentropic process, and 4 to 1 we are getting again isobaric process. So, these 4 processes, these 1 2, 2 3, 3 4 and 4 to 1 are considered in case of Brayton cycles. For ideal Brayton cycles 1 2 and 3 4 are isoentropic processes, but just like Rankine cycle, in reality these are different from the ideal conditions to some extent for every operations, because of different types of losses, frictions, etc. So, in this case we see if we have Q input here and Q output here, and this P is constant here, P is constant here also. So, this is a P1 and this is a P2. So, P1 and P2, that means we have one gas turbine it is giving us some exit gas, exhaust gas with P, and it is having a P1. Before that we are using some air and some combustion chamber, say it is a syngas. So, air heated, so P1 is increasing. So, now this P1 and this is your P2. So, the efficiency of this process is equal to 1 minus T1 by T2 was equal to 1 minus P1 by P2 to the power 1 minus gamma to the power gamma. So, this gamma is equal to heat capacity ratio, that is specific heat at constant Cp and Cv, constant pressure and Cv, this ratio is gamma. So, from this expression we see that if T2 value is higher, if T2 is very high, then efficiency will be higher. Similarly, if P2 value is high, then also efficiency will be higher. Thus, the P2, this is P2, this is P1. So, this P2 value which we are getting after combustion of the syngas or some we can have any other auxiliary fuel. So, this fuel will give us some combustion here in this chamber and a constant pressure will be maintained, that will release the flue gas to the gas turbine. So, that pressure is higher pressure than the pressure which is having here. So, this ratio, more the ratio will be, more the value of P2 will be giving us more efficiency. Similarly, more the temperature here will be giving us more efficiency, but how much temperature we can apply, that is limited by the material of constructions of the reactor of the system. It is around say 1500 to 1800 degree centigrade, and this pressure P2 by P1, this P2 that is 16 time of P1, 11 to 16 time of P1, this is normally used. Now, in the Brayton cycle ideal cases we have seen 2 isentropic process and 2 isobaric process, that is 1 to 2 and 3 to 4 isentropic, 2 to 3 and 4 to 1 isobaric, but in reality we will not get any isentropic process, those will be adiabatic process, isobaric process and isobaric process 3 and isobaric process 4 and 3 is adiabatic process. So, these are the real case Brayton cycle. Now, we will see how the efficiency can be monitored by using bottoming cycle or topping cycles. So, bottoming cycle, topping cycle and combined cycle, these 3 concept has come, 3 classifications of the cycles have thermodynamic cycles we have developed. So, one is your topping. So, topping cycle means we will be extracting mechanical and electrical energy first, then heat recovery. So, in this case we will use fuel, then it is combusted, then it will come and it will go to directly to turbine. So, obviously this is gas turbine. If required we will put here some supplementary fuel to increase the temperature of this flue gas generated here. If it is a gasifier then it will be syngas. So, oxygen will be sent and high temperature will be generated. So, this is turbine, electricity is produced first. Then turbine exhaust, this will be having also very high temperature and that will be used, this exhaust will be used for the heat recovery, waste heat recovery. So, water will be sent through this heat exchanger or boiler and then we will get steam or hot water and then we will the exhaust from this, it will be exhaust to air, some cleaning is required here, gas cleaning. So, this is your topping cycle and this is the bottoming cycle. So, bottoming cycle what will be happening? We will be producing heat first, say here it is the furnace. So, fuel is coming, combustion is taking place. So, we may supply some supplementary fuel to increase the temperature here and it will come to the heat recovery unit, that is boiler. So, boiler will send water, so that water will be converted to steam and steam will be used to produce electricity through the steam turbine, and the flue gas from the boiler will be go to stack for your treatment. So, this is called bottoming cycle. So, the combined cycle means both topping and bottoming cycles will be used simultaneously, and in this case we will get, so gas turbine exhaust can be used to produce steam for Rankine with additional fuel burning. So, in the first case we have here the turbine exhaust, it is going here and we are producing steam or hot water. In place of this, if we use the steam for electricity production using steam turbine again, so then this will be called as combined cycle. Now, by using different cycles and number of turbines we can improve the efficiency. Another approach is also there to improve the overall efficiency of the process, that is your cogeneration and additional heat recovery. So, cogeneration we can use the flue gas for the production of steam, we can or production of heat, or we can use it for the production of electricity. So, cogeneration means we will produce electricity as well as we will produce heat or will steam. Okay. In this case the efficiency increases. So, we have two options, either we can use electricity plus heat or electricity plus heating plus cooling. So, two situations may be available there. So, the third case, the tri-generation or combined cooling, heat and power applications, these refer to simultaneous generation of electricity and useful heating and cooling. So, just we have discussed in the beginning of this module that some part optional from turbine to cooling and then it is heated and it is to the boiler, recycle back to the boiler. So, this is one example of tri-generation, and tri-generation improves the efficiency, and here the overall efficiency is equal to not only the work at turbine, it is also the work for heating and cooling divided by Q input, total input we are giving. So, that is why in this case we get more overall efficiency of the plant. This is some example the how the combination of this steam generation, heat generation and electricity generation improves the efficiency. If it is a only heat production, maximum 80%, steam 80%, but power is 30%, only power 35% efficiency, but steam and heat separately gives more efficiency. But you can combine these two, either say steam and power or heat and power, then also we get intermediate overall efficiency, and this is your maximum efficiency we are getting here, that is heat and power. So, heat and power, this combined heat and power applications gives maximum efficiency. So, efforts are going on to get maximum efficiency and to improve the efficiency of the power plant. So, up to this in this module and in this part, and the second part we will discuss on overall efficiency of power plant and about different losses. So, thank you very much.